What if the universe ended right now, and you didn't even see it coming? No asteroids. No warning. Just a microscopic glitch in physics erasing your atoms at the exact speed of light. Forget the peaceful pale blue dot. The universe is a hostile machine, and today, we are stepping beyond the event horizon to expose its most violent anomalies. The contemplation of our cosmic standing begins with a profound realization that the entire history of human civilization, with all its triumphs and tragedies, is contained within a single pixel of light in the vast cosmic dark, a perspective famously described as the pale blue dot. As humanity moves away from the comfort of reassuring fables and toward the hard truths of objective insignificance, the universe is revealed not as a backdrop for human endeavor, but as a vast arena where we are merely the custodians of life's meaning. This realization stirs a distinct tingling in the spine as we approach the greatest of mysteries, floating like a mote of dust in the morning sky of an incomprehensible reality. We must acknowledge that the human race is, in a fundamental physical sense, a form of chemical scum residing on a moderate-sized planet that orbits an average star in the suburbs of one galaxy among hundreds of billions. While our daily mornings remain devoid of the extreme physics that govern the infant universe, a deeper investigation reveals that we are star stuff seeking to comprehend the symphony of strings that constitutes physical reality, a quest for the cosmos to understand itself through the emergence of consciousness. The architecture of the universe at its most massive scales defies any intuitive sense of organization, transitioning from the familiarity of individual galaxies to the terrifying dimensions of cosmic filaments that challenge our standard models of cosmology. In February 2025, a team of scientists led by Hans Boehringer at the Max Planck Institute for Extraterrestrial Physics unveiled the Quipu superstructure, the largest cosmic structure ever reliably characterized to date. Named after the ancient Andean system of knotted cords, Quipu is a staggering chain of 68 galaxy clusters linked together in three-dimensional space, extending over a physical length of approximately 1.4 billion light-years, or 428 megaparsecs. The sheer mass of this entity is estimated at 200 quadrillion solar masses, which represents a concentration of matter roughly 200,000 times the mass of the Milky Way galaxy. This discovery was made possible through the Cosmic Large-Scale Structure in X-rays, or CLASSICS cluster survey, which utilized data from the Rosat X-ray satellite to map the matter density distribution across nearly 86% of the sky. The existence of such a massive structure is significant because it challenges the prevailing Lambda Cold Dark Matter model, as such vast concentrations of matter were predicted to be far rarer in the current epoch of universal expansion. The implications of the Quipu superstructure extend into the very foundation of how we measure the universe, as structures of this magnitude leave a distinct imprint on the cosmic microwave background through the integrated Sachs-Wolf effect. As photons from the early universe pass through the massive gravitational well of Quipu, they gain energy falling in and lose it as they climb out. But because the universe is expanding, the well flattens during the transit, resulting in a net change in energy that manifests as temperature fluctuations. While the signal detected in the Planck satellite data matches theoretical predictions, it remains at a low significance, prompting further investigation into the true distribution of matter across the cosmic web. Furthermore, the presence of these invisible continents of galaxies complicates the determination of the Hubble constant, which describes the rate of universal expansion, by generating large-scale streaming motions. Galaxies are essentially caught in a gravitational tug-of-war, being pulled toward mass concentrations like Quipu with velocities that must be carefully accounted for to avoid distortions in our cosmological measurements. Shifting our focus to the local cosmic neighborhood, the Milky Way is not a solitary wanderer but a resident of the Laniakea Supercluster, a name meaning immense heaven in Hawaiian. Spanning approximately 520 million light-years and encompassing nearly 100,000 galaxies, Laniakea is defined by its basin of attraction, a region where all galactic motions are directed inward toward a gravitational focal point known as the Great Attractor. This gravitational anomaly is located roughly 220 million light-years away in the direction of the Centaurus and Norma clusters, possessing a mass estimated at a quadrillion suns. Despite its immense pull, the Great Attractor remains difficult to study because it lies within the Zone of Avoidance, a section of the sky obscured by the thick dust and gas of our own galactic disk. Recent observations have revealed that Laniakea itself is moving toward an even larger mass concentration known as the Shapley Supercluster, suggesting a hierarchical structure of cosmic attractors where each basin is nested within a larger one. However, in the ultimate battle between gravity and the repulsion of dark energy, expansion appears to be winning, as Laniakea is projected to eventually be torn apart and diluted into the cosmic void. Descending from the scale of superclusters to the extreme physics of individual stellar remnants, we encounter magnetars, the universe's most violent magnets. These specialized neutron stars possess magnetic fields that are a trillion times stronger than the magnetic field of the Earth, measured at extreme levels. The formation of a magnetar occurs during a supernova when a massive star collapses into a city-sized sphere of neutrons. If the newly formed star possesses the perfect combination of rapid spin and high temperature, a dynamo mechanism amplifies its magnetic field to these lethal levels. Within the vicinity of a magnetar, the laws of chemistry are effectively suspended as atoms are deformed into long, needle-like shapes, with hydrogen atoms becoming 200 times narrower than their normal diameter. The vacuum of space itself becomes polarized in these fields, behaving like a crystal that can split light photons in two. The most spectacular display of this power is the starquake, a rupture in the star's rigid crust that releases massive flares of gamma rays, such as the 2004 flare that released as much energy in a fraction of a second as the sun provides in 250,000 years. The year 2025 has also been defined by the resolution of a major paradox involving the earliest objects in the universe, discovered by the James Webb Space Telescope and known as little red dots. These compact, infrared bright objects from the very early universe, appearing as they were only 600 million to 1.5 billion years after the Big Bang, initially threatened to overturn our understanding of galaxy formation. The leading theory proposed in 2025 is that these dots represent a new class of object called the black hole star, where a supermassive black hole is embedded within a thick, turbulent gas shell or envelope. This configuration heats the surrounding gas until it glows with a characteristic red signature, allowing black holes to grow much faster than the galaxies that host them. This overmassive nature challenges the prevailing theory that black holes and galaxies grow in lockstep, suggesting that in the infant universe, these burgeoning giants essentially got ahead of their hosts. A specific case, the galaxy Virgil, appears as a typical young galaxy in visible light but transforms into a cosmic beast in the infrared, harboring a hidden black hole far larger than models would typically allow. One of the most extreme examples of this phenomenon is an object nicknamed the Cliff, which was flagged in July 2024 as a crucial test case for understanding the little red dot population. The Cliff is so distant that its light took 11.9 billion years to reach Earth, corresponding to a redshift of 3.55. It earned its name from a dramatic feature in its spectrum known as a Balmer break, a steep rise in luminosity in the ultraviolet region that is far stronger than what is observed in ordinary galaxies. Analysis in 2025 revealed that this record-breaking break is approximately 6.9, roughly 2 times stronger than any previously reported high redshift galaxy, and cannot be explained by any plausible stellar population model. Instead, the data is best fitted by a model where a central ionizing source, such as an accreting supermassive black hole, is enshrouded in a dense, spherical, and turbulent gas envelope with hydrogen densities reaching extremely high atomic concentrations. This confirms that at least some of these early objects are not ultra-dense stellar systems, but are instead powered by hidden engines that reprocess radiation through thick layers of gas. The sheer scale of these gravitational monsters is further exemplified by the ultramassive black holes that populate the centers of the most massive galaxies. While the Milky Way's central black hole is a respectable 4.5 million solar masses, Tonnenstilla 618 currently holds the record for one of the most massive black holes known, weighing 66 billion times the mass of the Sun. In August 2025, astronomers reported a significant breakthrough by directly measuring the mass of a black hole at the heart of the cosmic horseshoe galaxy system. By combining stellar velocity measurements with the analysis of gravitational lensing, where the black hole's gravity warps the light of a background galaxy into a nearly perfect Einstein ring, the team confirmed a mass of 36 billion suns. This behemoth is close to the theoretical upper limit for black hole mass and is approximately 10,000 times heavier than the black hole at our own galactic center. Such overmassive black holes in the local universe likely represent the descendants of the rapid growth phases observed in the early universe, potentially forming through the merger of multiple galaxies in fossil groups over billions of years. Not all black holes remain anchored to the centers of their galaxies. Some go rogue as wandering entities drifting through the cosmic suburbs. In September 2025, researchers identified a rare wandering black hole in the dwarf galaxy Manga 12772-12704. Located approximately 230 million light-years away. Unlike typical black holes, this intermediate mass giant, estimated at 300,000 solar masses, is offset from the galactic center by nearly 3,000 light-years. Despite its displacement, it remains actively accreting material and launching powerful radio jets, reaching temperatures exceeding 1 billion kelvins. This discovery provides direct observational support for the idea that black hole growth is not confined to galactic centers and that these lost travelers can quietly reshape their host galaxies from the outskirts through high-energy outflows. Such rogue black holes are likely launched by gravitational recoil during galaxy mergers or through multi-body interactions, suggesting that the population of invisible black holes in the universe may be far larger than previously estimated. The environment immediately surrounding these supermassive black holes is characterized by the quasar, the most luminous class of objects in the universe. Powered by the accretion disks of supermassive black holes, quasars convert gravitational energy into heat and light through intense friction as gas and dust spiral inward at nearly the speed of light. The first quasar identified, 3C273, remains a benchmark for these extremes, with temperatures at its heart climbing as high as 18 trillion degrees Fahrenheit, or 10 trillion degrees Celsius. Quasars are so powerful that they outshine all the stars in their host galaxy combined by a factor of 100, acting as high-energy regulators that blow away the gas required for star formation, effectively quenching galactic growth. In 2025, the DESI survey mapped 1.6 million of these nuclear furnaces, providing a three-dimensional map of the cosmos that reveals how quasars have shaped the distribution of matter since the universe was in its infancy. By observing how quasar light is absorbed by distant gas clouds, astronomers can use them as cosmic flashlights to probe the otherwise dark voids between galaxies. The year 2025 also brought a surprise visit from the interstellar medium in the form of Comet 3I/Atlas, the third known interstellar object to enter our solar system after Oumuamua and 2I/Borisov. Discovered on July 1, 2025, by astronomer Larry Deno, 3I/Atlas moved on a severely hyperbolic trajectory with an eccentricity of 6.28, far exceeding that of previous visitors and confirming its origin from outside the solar system. Observations by the Very Large Telescope and the James Webb Space Telescope revealed that 3I/Atlas possessed an unprecedented chemical signature, including a carbon dioxide to water ratio of nearly 20:1 and the surprising detection of nickel vapor at a distance of 3.88 astronomical units from the Sun. This nickel emission, detected without corresponding iron signatures, challenges conventional models of cometary metal liberation, which typically require high temperatures to sublimate metals from minerals. Instead, researchers propose that the nickel is released through the photodissociation of volatile molecules like nickel tetracarbonyl, a process that can operate in the frigid conditions of the outer solar system. This pristine object likely originated billions of years ago in the circumstellar environment of an asymptotic giant branch star, making it one of the oldest macroscopic things ever observed in our solar system. In late 2025, the James Webb Space Telescope further challenged our timeline of cosmic maturation with the discovery of the Alkananda galaxy, one of the most distant grand design spiral galaxies ever observed. Named after a Himalayan river, Alkananda existed just 1.5 billion years after the Big Bang, yet it displays a mature, beautifully structured spiral shape remarkably similar to the Milky Way. Spanning approximately 30,000 light-years, the galaxy features two symmetric spiral arms and a well-defined central bulge, defying models that predicted the early universe should only host chaotic and irregular structures. Alkananda is an impressive powerhouse, forming stars at a rate of 63 solar masses per year, which is 20 to 30 times faster than the current rate of the Milky Way. The discovery suggests that sophisticated galactic processes, such as gas accretion and disk settling, could operate far more efficiently in the early universe than previously thought. Half of Alkananda's stars appear to have formed in a mere 200 million years, indicating that the universe matured at an unexpected pace, potentially through smooth gas accretion rather than major collisions. The diversity of worlds revealed in 2025 extends to exotic exoplanets like the superpuffs of the Kepler-51 system, which have been nicknamed cotton candy planets due to their extremely low densities. These planets possess masses only a few times that of Earth, but have atmospheres of hydrogen and helium so bloated that they appear as large as Jupiter. With densities as low as 0.1 grams per cubic centimeter, these superpuffs represent a transient stage of planetary evolution where young worlds haven't yet lost their massive gas envelopes to the radiation of their host stars. Simultaneously, the search for life reached a vintage year in 2025, as the Perseverance rover found potential biosignatures in a Martian rock called Chiava Falls. These leopard spots, associated on Earth with chemical reactions that sustain microbial life, were found alongside organic molecules and evidence of liquid water, making it the most compelling hint yet of ancient life on our neighboring planet. Additionally, the detection of dimethyl sulfide on the exoplanet K2-18b, a gas produced only by marine phytoplankton on Earth, has sparked intense scientific debate over biological markers on a world 120 light-years away. The ultimate extreme of physical reality is not the scale of a superstructure or the heat of a quasar, but the potential for the absolute end of physics through vacuum decay. This theory centers on the Higgs field, which gives particles mass and dictates the laws of nature as we know them. Current measurements suggest the Higgs field may exist in a state of false vacuum, sitting on a metaphorical pedestal rather than the true lowest energy state. If the field were to tunnel to a lower energy state, it would create a bubble of true vacuum expanding at the speed of light, instantaneously rewriting the laws of physics and potentially causing atoms to fall apart without warning. While this scenario is terrifying, the universe has remained in its current state for 13.8 billion years, a fact that Stephen Hawking described as a remarkable example of cosmic fine-tuning. This precarious stability suggests that we exist in a transient window between the cosmic dawn and an unpredictable future. If vacuum decay does not occur, the universe faces a slow death through entropy in a scenario known as the Big Freeze or heat death. As the expansion of the universe continues to accelerate, galaxies will drift beyond the cosmic horizon and stars will eventually exhaust their fuel, leaving behind only dead remnants like white dwarfs and neutron stars. Over an unimaginably long period of years, even the most massive black holes will evaporate through Hawking radiation, eventually returning their content to the universe as a sea of photons. Once the last black hole has vanished, the universe will reach a state of thermodynamic equilibrium where entropy can no longer increase and the arrow of time ceases to have meaning. In this final state, the universe becomes a perfectly still, dark room, cooling toward absolute zero where nothing ever happens again, marking the end of the grand cosmic story. Reflecting on our cosmic standing, the exploration of these extremes, from the 200 quadrillion solar masses of Quipu to the 18 trillion degree heat of 3C273, serves to recalibrate our understanding of significance from human self-importance to cosmic humility. While we live on an insignificant planet of a humdrum star, we must find joy in the fact that we are the means by which the universe understands its own symphony of strings. The 2025 discoveries, such as the potential biosignatures on Mars and K2-18b, suggest that while we are small, we may not be alone in this vast arena. Consciousness is a temporary structure on the road from order to disorder, but it is the phenomenon that gives the universe its purpose. Ultimately, our responsibility is to preserve our fragile pale blue and to deal more kindly with one another. For in 100 billion galaxies, there is no hint that help will come from elsewhere to save us from ourselves. The quest for an ultimate theory will never end, for without the mystery of the unknown, the human spirit would stagnate.